Welcome! Today, we'll be tackling the popular problem number 26, remove duplicates from sorted array. This problem is a classic coding exercise that tests your understanding of array manipulation and in-place algorithms. Let's dive in and explore how we can efficiently solve this step by step. In this problem, you're given an integer array, nums, that is sorted in non-decreasing order. Your task is to remove duplicates from this array in place, meaning you cannot create a new array to store the result. Each unique element from the array should appear only once, and their relative order must remain the same. Since you cannot change the length of the array in some programming languages, the resulting unique elements must be placed in the beginning of the array, occupying the first k positions. The remaining elements beyond these k positions are irrelevant for this problem. Your goal is to return the value of k, representing the number of unique elements, while ensuring that the first k elements of the array contain the unique values in the correct order. Additionally, you must achieve this using O(1) extra memory, modifying the input array directly without allocating extra space. The output of the function should include two key pieces of information. First, you need to return the integer k, which represents the number of unique elements in the array after duplicates have been removed. Second, the first k elements of the modified nums array should contain these unique elements in the same order as they originally appeared. Any elements in the array beyond the first k positions do not matter and can be ignored. Let's understand this further with some examples. For instance, if the input array is nums equals 1, 1, 2, the output should be k equals 2 and the modified nums array should look like 1, 2, underscore. The underscore here represents that the values beyond the first k positions are irrelevant. The unique elements, 1, 2, are preserved in their original order. Now, consider another example where the input array is nums equals 0, 0, 1, 1, 1, 2, 2, 3, 3, 4. In this case, the output will be k equals 5 and the modified nums array will look like 0, 1, 2, 3, 4, underscore, 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 underscore. After removing duplicates, the unique elements 0, 1, 2, 3, 4 occupy the first k positions, and their order is preserved. The underscores signify that the values beyond these positions are irrelevant for our solution. Similarly, for a simpler case such as nums equals 1, 1, 1, 1, 1, the output will be k equals 1 with the modified array as 1, underscore, 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 underscore. Here, the array contains only one unique element, which is 1, and the rest of the elements can be ignored. Let's now look at the constraints and edge cases for this problem. The array nums has a length between 1 and 10⁻⁴, so you need to ensure your solution works efficiently for larger inputs. Each element in nums is an integer between -100 and 100, and the array is guaranteed to be sorted in non-decreasing order. Now, consider a few edge cases. For a single element array, such as nums equals 5, the output will be k equals 1, with the modified array being 5. Since there is only one element, it is already unique. Another edge case involves arrays where all elements are the same, such as nums equals 7, 7, 7, 7. Here, the output will be k equals 1, with the modified array being 7, underscore, 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 as only the first 7 is kept. We also need to address scenarios where there are no duplicates in the input array. For example, if nums equals 1, 2, 3, 4, the array already contains only unique elements, so the output will be k equals 4 and the modified array will remain 1, 2, 3, 4. The solution should ensure that arrays like this, which don't require any modifications, are handled correctly. For larger arrays, such as one with length 10⁻⁴ and repeated patterns, your solution must be able to efficiently identify the unique elements and handle the constraints. Finally, consider arrays that include negative numbers. For example, if nums equals -3, -3, -2, -1, -1, 0, 0, the output will be k equals 4 and the modified array will look like -3, -2, -1, 0, underscore, underscore, underscore. The solution must handle negative numbers correctly while preserving the order of unique elements. In summary, the problem requires you to remove duplicates in place from a sorted array while preserving the relative order of unique elements. You must modify the array directly without using extra memory, ensuring that the first k positions contain the unique values and returning k as the result. Edge cases, such as arrays with a single element, all duplicates, no duplicates, or negative numbers, must be handled appropriately. By considering these constraints and examples, you can efficiently solve the problem and handle the diverse scenarios that may arise. To tackle this problem, one straightforward idea is the brute force approach. The intuition here is simple. We iterate through the array and manually remove duplicates by shifting the elements whenever we encounter a repeated value. This can be done in two ways, either by creating a completely new array to store only unique elements or by modifying the existing array in place. The steps are as follows. First, traverse through the array and check if the current element already exists in the set of unique elements. If it's a duplicate, shift the subsequent elements to fill the gap left by the duplicate. While this does work, it comes with a significant drawback. The time complexity is O(n) squared, because every time we remove a duplicate, we need to shift elements, which can become very expensive for large arrays. The space complexity is O(1) if we modify the array in place, but it becomes O(n) if we use a new array to store unique elements. This approach is generally inefficient and only practical for very small input sizes. A more efficient solution is the two-pointer approach, which takes advantage of the fact that the array is sorted. Here, we use two pointers to efficiently overwrite duplicates while maintaining the position for unique elements. The key observation is that in a sorted array, duplicates will always appear consecutively. This allows us to traverse the array with one pointer, while another pointer keeps track of the position where the next unique element should be placed. Specifically, the slow pointer, denoted as I, tracks the last index of unique values, while the fast pointer, j, traverses the entire array. Whenever the element at nums, j, is distinct from nums, I, we increment the slow pointer, I, and update nums, I, with the value at nums, j. This process continues until we've processed all elements. The magic of this approach lies in its efficiency. It runs in O(n) time since each element is visited only once, and it requires O(1) additional space because all the operations are performed in place. The two-pointer approach offers a significant advantage for larger arrays due to its efficiency. By modifying the array in place, it avoids the overhead of creating additional data structures, making it highly suitable for scenarios where memory usage is a concern. However, there are trade-offs to consider. Modifying the array in place means that if the original order or structure of the array is needed elsewhere in the program, this approach may not be ideal. Alternatively, we could use a hash set to keep track of elements we've already seen. This simplifies the logic since we can just skip over duplicates during traversal. However, it requires additional memory to store the hash set, which violates the problem's constraint of performing the operation in place. The hash set approach involves traversing the array, adding elements to the set, and then reconstructing the array with only unique values. While the time complexity remains O(n), the space complexity increases to O(n), making it less optimal compared to the two-pointer method. The hash set approach, while straightforward, comes with clear disadvantages. Its reliance on additional memory makes it unsuitable for this problem, as the constraints explicitly require an in-place solution. By contrast, the two-pointer strategy aligns perfectly with the problem's requirements, offering an optimal balance between time and space complexity. The brute force method, though simple to understand, is far too slow for larger arrays due to its O(n) squared complexity, which involves repeated shifting of elements. The two-pointer method stands out as the best choice because it leverages the sorted nature of the array to minimize unnecessary operations. Key insights that inform this choice include recognizing that adjacent duplicates in a sorted array allow us to overwrite values efficiently, and the two-pointer technique ensures that each element is processed only once, making it both time-efficient and space-efficient. While the two-pointer approach is highly efficient, it does have some trade-offs. Specifically, modifying the array in place means that the original structure of the array is altered, which might be problematic if the original data is needed elsewhere. Additionally, while it's more complex to implement than the brute force approach, the added complexity is minimal and well worth the performance gain. Overall, the two-pointer method is the most practical and efficient solution for this problem. It strikes an excellent balance between time and space efficiency, adheres to the problem's constraints, and is capable of handling large input sizes with ease, making it the clear choice for implementation. In this problem, the objective is to remove duplicate values from a sorted array while ensuring that each unique element appears only once. The critical constraint is that this must be done in place, meaning we cannot use extra space. Additionally, the relative order of the elements must be preserved. To achieve this efficiently, we'll use the two-pointer technique. Here's how it works. We initialize 2 pointers, I and j. The slow pointer I will track the position of the last unique element we've identified, starting at index 0. The fast pointer j starts at index 1 and scans the array to locate the next unique element. As we traverse the array, we'll compare the values at these 2 pointers to determine whether we've encountered a duplicate or found a new unique element. Let's break this process down step by step. When checking for uniqueness, we compare the elements at I and j. If the value at j is different from the value at I, it means we've found a new unique element. In this case, we increment I to move to the next position where the unique element will be stored, and then assign the value at j to I. On the other hand, if the values at I and j are the same, it indicates a duplicate, so we simply increment j to continue scanning the array for the next unique value. There are a few edge cases to consider. If the array is empty, there's nothing to process, so we immediately return a result of 0. If the array has only one element, it's already unique, so we return its length as 1. Once we've traversed the entire array, all unique elements will be grouped at the beginning of the array, occupying the first I+1 positions. The result we return is the length of this unique section, which is also I+1. This ensures the algorithm completes efficiently while modifying the array in place. The two-pointer technique is particularly well suited for this problem because it allows us to modify the array in place without requiring additional memory. The slow pointer, I, ensures that unique elements are stored in order, while the fast pointer, j, scans the array for the next unique value. This approach is optimal because it avoids the need for auxiliary data structures like sets or hash maps, which would increase space complexity. By directly overwriting duplicates in the array, we maintain an in-place solution that adheres to the problem's constraints. In terms of efficiency, the algorithm has a time complexity of O(n), as each element in the array is processed exactly once. The space complexity is O(1), as the only additional storage we use is for the two-pointer variables. These properties make the two-pointer technique both efficient and elegant for solving this problem. The input array itself serves as the primary data structure for this algorithm. By modifying it in place, we store all unique elements at the beginning, ensuring minimal space usage. The two pointers, I and j, are simple integer variables that help track positions within the array. Let's consider an example to see this in action. Suppose the input array is 1, 1, 2, 2, 3, 4, 4. Initially, we set I to 0 and j to 1. The slow pointer I will track the position of the last unique element, while the fast pointer j scans for the next unique value. As we iterate through the array, we'll follow a systematic process of comparing the values at these pointers and updating the array as needed. Let's walk through the example step by step. First, compare ARR1, value 1, with ARR0, value 1. Since they are the same, it's a duplicate, so we increment j to move to the next element. Next, compare ARR2, value 2, with ARR0, value 1. These values are different, indicating a new unique element. We increment I to 1 and update ARR1 to store the value 2. The array now looks like 1, 2, 2, 2, 3, 4, 4. Continue comparing ARR3, value 2, with ARR1, value 2. Since they are the same, increment j again. Then, compare ARR4, value 3, with ARR1, value 2. These values are different, so increment I to 2 and update ARR2 to 3. The array becomes 1, 2, 3, 2, 3, 4, 4. Repeat this process until j reaches the end of the array. The final unique portion of the array is 1, 2, 3, 4, and its length is 4. Edge cases include scenarios like an empty array, where the result is 0, or a single element array, where the result is 1. If all elements are unique, the length of the array remains unchanged. If all elements are duplicates, only one unique value is retained, resulting in a length of 1. To optimize this algorithm further, we can take advantage of the fact that the input array is sorted. This ensures that duplicates are always contiguous, meaning we don't need to compare every pair of elements. Instead, the fast pointer naturally skips over duplicate values in a single pass. By leveraging this property, we minimize unnecessary comparisons and streamline the traversal process. This optimization doesn't alter the overall structure of the algorithm but enhances its efficiency, ensuring that the solution remains both time and space optimal. This Python implementation solves LeetCode problem number 26, remove duplicates from sorted array using the two-pointer technique. The function begins by handling the edge case where the input list is empty. If nums is empty, the function immediately returns 0, as there are no elements to process. Next, two pointers are initialized, I, slow pointer, and j, fast pointer. The slow pointer, I, keeps track of the position where the next unique element should be placed, while the fast pointer, j, scans through the array to find unique elements. The loop starts with j at 1, iterating through the rest of the array. For each iteration, the value at nums, j, is compared to nums, I. If the values are different, it means a new unique element has been found. The slow pointer I is increment, and nums, j, is copied to nums, I, effectively placing the unique element in its correct position. After the loop completes, the function returns I plus 1, which represents the count of unique elements in the modified array. Since I is 0-based, adding 1 gives the total count of unique elements. This approach ensures that the array is modified in place, using O(1) extra space. The time complexity is O(n), as the array is traversed once. This makes the solution both efficient and optimal for the problem statement. This is the Java implementation of LeetCode problem number 26, remove duplicates from sorted array. The logic mirrors the Python implementation, utilizing two pointers, a slow pointer to track the position of unique elements and a fast pointer to traverse the array. Key differences include Java's use of explicit type declarations, array handling, and class structure. The method updates the input array in place and returns the count of unique elements. In this example, we start with the input array nums equal to 1, 1, 2. Initially, the slow pointer I is set to 0, and the array is sorted, meaning any duplicates will be adjacent to each other. Now, in the first iteration, the fast pointer j starts at index 1 and checks the value at nums, 1, which is 1. It compares this value with nums, 0, which is also 1. Since the values are equal, there's no need to update anything, and we simply move the fast pointer j to the next index. In the second iteration, the fast pointer j is now at index 2, checking the value nums, 2, which is 2. This value is compared with nums, 0, which is 1. Since the values are different, this indicates we've found a new unique element. To handle this, we increment the slow pointer I to 1 and update nums, 1, to the value of nums, 2. The array now looks like 1, 2, 2. At the end of the process, the slow pointer I is at index 1, so the count of unique elements is I plus 1, which equals 2. The modified array 1, 2, underscore retains only the first two unique elements, and the rest of the array is disregarded. Now, let's consider a case where there are no duplicates in the input array. The array nums is 1, 2, 3, 4, and the slow pointer I is initialized to 0. In the first iteration, the fast pointer j is at index 1, checking nums, 1, which is 2. Comparing this with nums, 0, which is 1, we see that the values are different. Therefore, we increment I to 1 and set nums, 1, to nums, 1. Since the value remains unchanged, the array stays as 1, 2, 3, 4. In the second iteration, the fast pointer j moves to index 2, checking nums, 2, which is 3. This is compared with nums, 1, which is 2. Again, the values are different, so we increment I to 2 and set nums, 2, to nums, 2, leaving the array unchanged. In the third iteration, the fast pointer j moves to index 3, checking the value nums, 3, which is 4. This is compared with nums, 2, which is 3. Since the values differ, we increment the slow pointer I to 3 and set nums, 3, to nums, 3. Again, no changes are made to the array, as the value remains the same. At the end of this process, the slow pointer I is at index 3, so the count of unique elements is I plus 1, which equals 4. The modified array remains 1, 2, 3, 4, and since there were no duplicates to remove, all elements are relevant and unchanged. Let's now examine a case where the input array consists entirely of duplicates. Here, nums is 2, 2, 2, 2, and the slow pointer I is initialized to 0. In the first iteration, the fast pointer j is at index 1, checking nums 1, which is 2. This is compared with nums 0, which is also 2. Since the values are equal, no updates are made, and the fast pointer j advances to the next index. In the second iteration, the fast pointer j is at index 2, checking nums 2, which is again 2. This is compared with nums 0, and since the values are still equal, no action is taken and the fast pointer moves to the next index. In the third iteration, the fast pointer j is now at index 3, checking nums 3, which is 2. This is compared with nums 0, and once again, since the values are equal, no updates are made. The fast pointer has now completed scanning the array. At the end of this process, the slow pointer I remains at index 0, meaning there is only one unique element in the array. The count of unique elements is therefore I plus 1, which equals 1. The modified array is 2, underscore, 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 where only the first element is relevant, and the rest are ignored. To summarize, the slow pointer I helps keep track of the position of the last unique element, while the fast pointer j scans for new unique values. By overwriting duplicates in place, the solution achieves efficiency without using additional space. The return value represents the count of unique elements, not the modified array itself. The time complexity of this solution is O, n, where n is the length of the input array, nums. Let's break it down step by step. First, initializing the pointer I, also known as the slow pointer, takes constant time, O1. Then, we have the for loop, which iterates through the array from index 1 to the end. This loop runs exactly n1 times, as it starts at the second element. Within each iteration, the condition nums, j equals nums, I, is checked, which is a simple comparison and takes O1. If the condition is true, we increment the pointer I and assign nums, j, to nums, I, and both of these operations also take constant time, O1. Since the operations inside the loop are O1, for each iteration, the total work done over n1 iterations is O(n1), asterisk O1, which simplifies to O(n). Finally, the return statement, which returns the value I plus 1, is a constant time operation, O1. Putting it all together, the overall time complexity of the solution is O(n). Therefore, the time complexity remains O(n), as the algorithm only passes through the array once. Now, let's discuss the space complexity. The space complexity of this solution is O(1), because the algorithm does not use any additional data structures. Instead, it modifies the input array nums in place. It only requires two pointers, I and j, to track positions within the array, and these pointers consume constant memory, O1. No auxiliary space or additional lists are allocated during this process, which means the memory usage remains fixed regardless of the size of the input. Next, if we analyze the best, average, and worst case scenarios, the time complexity remains the same in all cases because the algorithm always iterates through the entire array. In the best case, where all elements in nums are unique, the loop still performs n1 iterations. In the average case, where duplicates are distributed randomly, the runtime is still determined by the single pass through the array, making it O(n). Even in the worst case, where all elements in nums are duplicates, the loop still processes every element, resulting in the same O(n) time complexity. In summary, the algorithm is efficient across all scenarios, with linear time complexity and constant space complexity. To better appreciate the efficiency of this approach, let's compare it to a brute force method. A naive solution would involve creating a new list to store unique elements. For each element in the original array, you'd check if it's already present in the new list. This requires nested iterations, one to traverse the array and another to check for duplicates in the new list. Consequently, this approach has a time complexity of O(n squared). Additionally, because it requires a new list to store unique elements, the space complexity would be O(n). In contrast, the optimized two-pointer approach eliminates the need for extra space by modifying the input array in place, reducing the space complexity to O(1). By maintaining two pointers and only performing a single pass through the array, the time complexity is significantly reduced to O(n). This makes the two-pointer method much more efficient in both time and space. Mathematically, the Big O analysis confirms this. Since the algorithm traverses the input array once, performing O(1) operations for each element, the total operations sum to n asterisk O(1), which simplifies to O(n). With no additional memory allocations beyond the 2 pointers, space complexity remains O(1). Clearly, this optimized solution is both time-efficient and space-efficient compared to the brute force approach, making it a superior choice for this problem. When working on removing duplicates from a sorted array, there are a few common mistakes to watch out for. First, modifying the array directly during iteration can cause issues. For example, if you try to remove elements with methods like del in Python or remove in Java while looping, you might unintentionally skip elements or even encounter index out-of-bound errors. Instead, it's better to use a separate pointer or data structure to track progress. Another pitfall is neglecting edge cases. Scenarios like an empty array, a single-element array, or arrays where all elements are unique need careful handling to avoid incorrect results or runtime errors. Finally, avoid overusing nested loops for this problem. A brute force approach with O(n)² complexity might work for small inputs, but for large arrays, like those with tens of thousands of elements, it can lead to time limit exceeded errors. Instead, focus on more efficient methods like the two-pointer technique. Another mistake to avoid is failing to preserve the input order when it's required. If you use a hash set or sort the array to remove duplicates, the original order might be lost, which could violate the problem's constraints. Always check whether maintaining the order is a requirement. Additionally, be cautious about space complexity assumptions. Some solutions, like using hash sets, might seem efficient but aren't truly in place since they require extra memory. Remember, in place typically means O(1) space beyond the input array. Pay close attention to these constraints when working on space-optimized solutions. In interviews, this problem often tests your ability to recognize patterns and optimize solutions. The two-pointer technique is a favorite here due to its efficiency and minimal space usage. It's important to understand this method well and be able to explain it clearly. Interviewers may also ask you to discuss trade-offs. For example, while a hash set approach allows faster lookups, it uses extra space, whereas the two-pointer technique is more space-efficient but slightly slower in some scenarios. Always clarify constraints with the interviewer, such as whether the array is sorted or if there's a specific return format. This helps ensure you don't make incorrect assumptions. Optimization is a key focus in interviews, so start with a simple brute force solution and then refine it step by step. Lastly, be prepared for follow-up variations, like counting duplicates, removing duplicates from unsorted arrays, or handling cases where duplicates might appear up to k times. This problem is closely related to several others that you might encounter. For instance, LeetCode 26, which we're discussing, is the classic example of using the two-pointer technique to remove duplicates. A common variation is LeetCode 80, where you're allowed at most 2 duplicates instead of none. Another similar problem is LeetCode 83, which applies the same concept to linked lists instead of arrays. Finally, LeetCode 217 focuses on detecting duplicates rather than removing them, and it often involves hash sets or sorting to identify repeated elements. Understanding these related problems can deepen your grasp of the underlying concepts and prepare you for variations in interviews. There are multiple approaches to removing duplicates, each with its own trade-offs. The two-pointer technique is a highly efficient method for sorted arrays. It operates in O(n) time and uses O(1) space, making it both fast and space-efficient. However, it requires careful handling of pointer manipulation. If the array is unsorted, a hash set or hash map can be used, offering O(n) time complexity as well, but requiring additional memory, which results in O(n) space complexity. Another option is sorting the array first and then iterating to remove duplicates. This has a time complexity of O(n) log n due to the sorting step, and if sorting is done in place, it uses O(1) additional space. While slower, this approach can be useful in scenarios where the input is not sorted and maintaining order is not a concern. Choosing the best approach depends on the specific constraints and requirements of the problem. Great work! To summarize, we learned how to efficiently remove duplicates from a sorted array using in-place techniques. Remember, mastering these approaches is crucial for solving problems with memory constraints. If you enjoyed this, don't forget to subscribe for more coding solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!